Hi everyone, I am Dean Kang. Today, I wish to introduce work named Transcrowd++, Images Crowd Counting Using Transformer. This work is joint with Xiu Chen, Wei Xiu and Xiang Bai. Three of us are from Hwaseong University of Science and Technology, and Wei Xiu is from Beijing University of Posts and Telecommunications. The presentation follows this outlined background. Our methods, results, limitation and outlook. We will also show some visualizations for you. This year, the Visdrone 2021 Crowd Counting Challenge requires participating algorithms to count persons in each pair of RGBT images. Here, RGBT means the RGB and thermal images. When only using optical information of RGB images, we cannot effectively recognize the person in poor illumination conditions. When only utilizing thermal images, some negative heating objects are hard to be distinguished. The mainstream crowd counting methods directly leverage the deep neural network to regress a density map. This map is generated by the accumulation of Gaussian functions, and the pixel value represents the people number in each pixel. The prediction count can be obtained by summing the density map. Even though deep neural networks have achieved significant progress, there are still many challenges, such as scale variations, density variations, illuminance variations and blur. Here, we choose the RGB images for illustration. As shown in these images, scales are various. This is at a low altitude, and this is from a high altitude. As for the density variations, this is very dense, while this is sparse. As well as the illuminance can be very dark. Besides, some images show strong blur and disorder. There are two pipelines for the cross-modal collaborative representation learning framework. One is to fuse features, as shown in Figure A. The framework consists of multiple modality branches, and some information fusion modules to share complementary information of different modalities. Another is directly to fuse results between two individual modalities, and each modality will pass an individual network, as shown in Figure B. The final result can be obtained by using the average or max operator. Which pipeline is better for this dataset? Well, we find that the pair of RGBT of images are not strictly aligned. Some of them exist the pixel shift. As shown in this figure, the point annotations are based on the thermal images, while the corresponding annotations of RGB images may be in the vacant space. If we choose to fuse the feature, we need to align the semantic feature in the same spatial, which is difficult only based on the point level annotations. Thus, we choose to fuse the final count from each individual modality. Recently, Vision Transformer has aroused great interest in the whole community, and shows promising results across many vision tasks. Our recent work Transcrowd is the first to explore the transformer into the crowd counting task, establishing the perspective of sequence-to-count prediction. The Transcrowd is designed for the weekly supervised crowd counting task, which cannot be directly used in this task. Hence, in this competition, we proposed the Transcrowd++, which is based on the Swin Transformer, a recent strong backbone. Due to the output size of Swin Transformer is only 1/32 of the input, we add a top-bottom fusion mechanism to make full use of the variant spatial information extracted from different stages of the backbone to generate high-quality density maps. During the training phase, we train an independent Transcrowd++ model for RGB and thermal modalities, respectively. During the testing phase, for each RGB or thermal modality, the prediction count is the average of the 5 predictions from the different stages. Well, for a pair of RGBT images, the final count is to choose the max value of count_R and count_T. Here, we also use two different losses, MSE loss and SIM loss. The MSE loss helps us get the density information, and the SIM loss helps us preserve the structure information. And the larger SIM value means less difference between the predicted density map and ground truth. The alpha is the weight to balance training. The follows. We introduce the external dataset. According to the test guideline, we can utilize external datasets. The Vistron 2020 dataset is also captured from the aerial view, which can be used as an external dataset for pre-training. This dataset only contains RGB images without thermal images. Hence, we adopt the DM cycle GAN to transform the RGB images into the thermal style images, as shown in this figure. Here, we summarize the experimental detail. Specifically, for both RGB and thermal images, we set the Gaussian kernel as 4. We augment the training data by horizontal flip, random brightness, saturation and contrast changing, adding noise. Additionally, we scale all images by 1.5 times offline to add more samples. We randomly choose 1/10 of the training set for validation. The backbone is initialized from a pre-trained Swin Transformer based on the ImageNet 22K database. The rest layers are initialized by a Gaussian distribution, using the mean of 0 and the standard deviation of 0.01. The balance weight alpha is set as 10. The atom is used to optimize the model with the learning rate of 0.0001, and the weight decay is set to 0.0005. We set the training batch size to 24, and the crop size is 384 times 384. Here are our results. We get first place in this challenge, reporting the 9.59 mean average error on the test set. We further analyze the different fusion mechanisms. Only using RGB images, we cannot achieve a considerable result because the dataset contains many images, which from extremely dark scenes. Using the thermal modality, we can achieve a relative performance improvement of 17.3%. Using two modalities, we find that simply using the max operator can achieve the best result. Besides, the IADM fusion mechanism and average operator are similar. We also test our method on the RGBT-CC crowd dataset, which is a large-scale RGBT crowd counting benchmark, containing 2030 pairs of RGB thermal images, with 138,389 annotated people. Note that we do not use external datasets for pre-training in this dataset. We can see that the proposed method also achieved the best result. Here are some visualizations from the validation set. As we can see in the first row, the best result is from the RGB images since the thermal images contain some confusing areas. For the second row, the best result is from the thermal images. Obviously, this RGB image is an extremely dark scene, which hard to recognize the crowd, while the thermal image presents precise instance locations. Thus, for this case, the best result is from the thermal image. For the third row, the prediction results from RGB and thermal images are very similar, and the thermal image is slightly larger than the RGB images. Then the network will also choose the prediction result from the thermal image as the final count. Finally, we summarize the limitation of the proposed method in given outlook. Specifically, the proposed method contains about 90 M parameters, which is a big model compared with some popular counting methods. Transformer shows great potential in the crowd analysis task, such as crowd counting and localization, and we believe that the transformer-based methods still have a lot of room for improvement. Okay, that's all as our presentations. Thanks for your attention and listening.